Alright, so in this series on the Axiom of Choice, we've talked about the Hausdorff maximal principle, we've talked about Zorn's lemma, we've talked about the well-ordering principle, and now we are finally ready to talk about the Axiom of Choice. And again, what this says is that if we have a non-empty collection of non-empty sets, then the direct product of all of these sets is non-empty. And what we can do now is we can prove this from the well-ordering principle. So let X be the union of all of these X alphas. Now pick a well-ordering on X, and for every single alpha in A, let F alpha, so F is going to be an element of the direct product of all of the X alphas. So what this is saying is this is how we're choosing the alpha coordinate of F. And we choose it to be the minimal element of X alpha. Remember, X alpha is a subset of X. And so with it being a subset of X, it has a minimal element because that's what it means for X to have a well ordering. So then this F is an element of the direct product. And so think about what we discussed when we first brought up the axiom of choice. We talked about, well, it makes sense that it should be possible to construct an element of this direct product. And what you do is for every X alpha, or for the alpha coordinate, you just choose some element of X alpha. And the big question there, and the thing that was sort of, we didn't really think about, is how do you choose the element of X alpha? Because you have to, like, all of these X alphas can be really weird, and you have to choose an element of X alpha for every single alpha. And so it's not clear that there's a way to do this. Well, the well-ordering principle gives us a way to do it. You choose the element by choosing the minimal element of X alpha. But if you don't have the well-ordering principle, it's not clear that this should be the case. Or it's not clear that you should be able to do this. So anyways, the well-ordering principle implies the axiom of choice. Alright, so a corollary of this, if you've got a disjoint collection of non-empty sets, there is a set Y in their union which intersects at every single set at least once. You could sort of see this as sort of a restatement of 4, and the way you prove this, you take Y to be f of A, and F is in this thing. So yeah, it's pretty straightforward. Okay, so what do we have? We have, let's just write this out. So we have Hausdorff maximum principle implies and is implied by Zorn's lemma, so they're equivalent. Zorn's lemma implies well-ordering principle. Well-ordering principle implies axiom of choice. Okay, so now we have deduced the axiom of choice from the Hausdorff maximal principle. In fact, it can be shown that the two are logically equivalent. So we know that Hausdorff maximal principle implies the axiom of choice. In fact, we can prove that the axiom of choice implies the Hausdorff maximal principle. So all of these statements are saying exactly the same thing. They're all equivalent, even though they all seem like sort of weird and slightly different. They're all actually exactly the same thing. These are all equivalent statements. And so to prove that the axiom of choice implies the Hausdorff maximal principle, let's see here. We need to, so you could just find this, proofwiki.org. So basically, you look at this, blah, blah, blah. There's something here called transfinite induction. Okay, so basically, at this point, what I wanted to do is I wanted to make this like a complete series, and to complete it by like finishing the circle by proving that the axiom of choice implies a Hausdorff. Well, actually, implies Zorn's lemma, but again, Zorn's lemma is equivalent to the Hausdorff maximum principle. So if you deduce Zorn's lemma from the axiom of choice, you've still got this loop complete of all these things being the same. And transfinite this is transfinite recursion. Perhaps its axiom of choice implies Hausdorff maximal principle, which requires transfinite induction. But transfinite induction, transfinite incursion, it's sort of a weird logic thing that's sort of like an induction argument, but a more general version. So induction is you prove to prove that a property holds for every natural number n. You prove that the property holds for n equals 1, and then you prove that if it holds for n, then it holds for n plus 1. And then that you conclude that the property holds for every natural number n. Transfinite induction, I think, is sort of the same thing, but instead of like indexing these things by natural numbers, you can use like an arbitrary ordinal, or yeah, I don't know. I never really studied like ordinals and cardinal numbers and things like that. So basically, I would have to do a lot of work in order to be able to prove and show a proof that the axiom of choice implies Zorn's lemma. Maybe I'll do it someday and add it as an extra video to this series. But for now, we can sort of just trust logicians that they've found a way, or that there is a way to assume the axiom of choice and prove Zorn's lemma, in which case all of those things that we've talked about are equivalent. And in fact, there's a whole bunch of other statements which are equivalent to the axiom of choice, and here is a list of them just from Wikipedia. So again, here we see well-ordering theorem, Zorn's lemma, but we also see a lot of other interesting, so those are all things, Hausdorff maximal principle, all things that we talked about, but there's also a lot of other things that we haven't talked about. So Taikanof Serum, which is that the product of compact topological spaces is itself compact. Of course, here when we say product, you can take a product over an arbitrary collection, and so that's, again, sort of why we need to invoke the axiom of choice to prove that, and it turns out that can prove the axiom of choice. Another thing, every vector space has a basis. You don't need the axiom of choice to prove this for finite dimensional vector spaces, but particularly for infinite dimensional vector spaces, you need the axiom of choice. And just to look at this and get a flavor of this, I just found like a proof online, and you can just skim through this and sort of get a flavor for it. So what you do is you let A be the set of linearly independent subsets of X. So basically, and then for every totally ordered subset, you take their union to get an upper bound. So basically what this is saying is for your basis, you basically want a maximal linearly independent subset. And to get that, what you do is you want to apply Zorn's lemma. So what you do is you prove that every totally ordered subset of things which are sort of smaller versions of what you want, that every totally ordered subset of collections like that has an upper bound, and then you get your maximum element, which is the thing that you really want. And you can sort of see that in here in a lot of these situations, like Taikanof Serum, product of compact topologies is compact. You can sort of imagine what the flavor might be like. Maybe consider a totally ordered collection of products of compact topological spaces, and then sort of try to find some sort of maximal element. I think maybe that's the sort of thing. but again, every unital ring contains a maximal ideal. So I assume what you'd want to do is you take collections of ideals and you probably define a partial order on them, and then you prove that every totally ordered collection of maximal ideals or every totally ordered collection of ideals has an upper bound, and then you get your maximum element, which is your maximal ideal. All of these sort of have that sort of flavor to them. And so all these things that you see here happen to be equivalent. And now, but we still haven't answered the main question of, is this a true statement or is it a false statement? And for reasons which I will probably never understand, the truth or falseness of the axiom of choice is logically independent of all the other assumptions that we sort of use in mathematics. So mathematics is sort of based on set theory to some extent, and the typical model of set theory that we use is called Zermelo-Fraenkel. I should have probably figured out how to pronounce this before filming a video that involves talking. But it's ZF. So ZF is sort of this set theory thing that we use in math. And I don't know what all these... So the axioms are listed here. And it's basically... What it means is that this is a set theory in which sets behave the way that you would think they should behave. And so yeah, so this is the sort of like set theory that mathematicians typically use in their proofs. And it turns out that these assumptions are completely independent of the axiom of choice. So you can take all these set theory assumptions in ZF, and you can also assume that the axiom of choice holds, and then you get a perfectly reasonable set theory that you can use to prove statements. But you can also assume that the axiom of choice is not true, in which case you also get a set theory which you can work with. And so this is really interesting that in fact it's neither absolutely true or false. You sort of get to choose whether or not you want it to be true, based on whether you believe it should be true or not. I have no problem with using it, because there's a lot of things that it lets you do. Like, I like the fact that every vector space has a basis. I think that's a reasonable thing to expect. And also the axiom of choice itself, being able to choose an element of, or being able to take a direct product of a whole bunch of non-empty things and end up with something which is non-empty, I think that's perfectly reasonable. So I think I personally am fine with using it. However, there is sort of this idea that, like, if you're trying to prove a statement, and you prove it if you can prove a statement without using the axiom of choice, then you shouldn't prove it using the axiom of choice, because you're proving it using more firepower than you need and using more assumptions than you need. But there are some things where you absolutely need the axiom of choice to prove them. But yeah, so that's the axiom of choice. It is independent of standard set theoretical assumptions. You can assume that it's true, you can assume that it isn't true, and you can do perfectly fine mathematics. And it's really interesting to see that this is sort of a thing which is equivalent to a whole bunch of other potentially useful facts, which sort of are in this state of neither true or false. It's simply something that you can choose to include as a proposition in set theory or choose to not include. So yeah, that's I think a really important topic in mathematics, and even though it took some time to discuss it, there wasn't a ton of background that was necessary beyond standard set theory. So yeah, there you go. Now you understand a lot of how the axiom of choice works and what its place is in mathematics.